Hello, everyone, and welcome. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. Today's event focuses on DoD-funded research efforts to advance the characterization and management of submerged munitions in marine environments. Dr. Nina Stark from Virginia Tech will discuss the development of an improved framework for the deployment of a portable Freefall penetrometer for cost-effective and rapid characterization of munitions sites. Dr. Stark will also provide details on her research strategy, which included field surveys in areas of varying environmental conditions, laboratory testing, and the development and proof of concept of the framework involved in this project. Dr. Stark will pause midway through her presentation to answer questions, and we will conclude the webinar with a longer question and answer session. The next several slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you're unable to download Zoom, you can view the slide using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you continue having difficulties with the slides or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select the speaker and microphone, and follow the prompts as they appear in your screen. If you continue having difficulties, just call into the conference line shown here. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for Nina. And then in case of continued difficulties, keep in mind that you can download a PDF of the slides from the webinar webpage, and you can then call into the conference line provided to you in your webinar registration confirmation email. Note that we will be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here, and that's another option for viewing today's event. The broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A periods to submit your questions. We do encourage you to submit them well in advance of the Q&A sessions. And when you do submit your question, we request that you please add your organization name at the end of your question so that we can identify you during the Q&A session. And with that, I would like to introduce Dr. David Bradley, who is the SERDP and ESTCP Program Manager for the Munitions Response Program area. Dr. Bradley's professional career includes U.S. Navy-supported research, laboratory directorship at the NATO Undersea Research Center in Italy, and research academic activities at Pennsylvania State University's Applied Research Laboratory. An emeritus professor of acoustics, Dr. Bradley is currently an APL University of Washington staff member assigned to the SERDP ESTCP Program Office. He is a fellow of the Acoustical Society and has chaired society committees, including serving as president. Dave, please proceed.
Good morning, everyone, and thank you, Rula. Welcome to today's webinar. I can tell you that it is a critical aspect of understanding submerged munitions and their environment in the underwater circumstance. The program in general was established in 1991 by Congress, and it's a partnership between the Department of Defense, the Department of Energy, and EPA. The combination of programs, that is SERDP and ESTCP, are complementary, with much of the SERDP research occurring in the laboratory and at pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts in the transition process. There are 4 program areas in SERDP and 5 in ESTCP. The installation, energy, and water program is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapons systems and platforms, are in both SERDP and ESTCP programs managed jointly by particular program managers. The webinar today is focused on research and demonstrations that were carried out under munitions response, which has 2 components. Historically, it was focused on land efforts or terrestrial efforts, and currently the focus is on munitions underwater. The webinar series highlights research and demonstration efforts from each of the 5 program areas. And you can see a partial list on the screen at the moment. You can find additional information about upcoming webinars at this link. And I will close with pointing out that we have an annual symposium. This year it's from November 30th through December 3rd. I would encourage and welcome your participation in that symposium. Interest and additional efforts are most heartily welcomed. And with that, I'll turn it back to Rula.
Thank you so much, Dave. It is now my pleasure to introduce today's featured speaker, Dr. Nina Stark, who is an associate professor in the Department of Civil and Environmental Engineering at Virginia Tech in Blasburg, Virginia. Dr. Stark's current areas of research focus on the in-situ geotechnical characterization of riverine, estuarine, coastal, and seafloor sediments, the correlation of geotechnical sediment properties and remotely sensed seabed and coastal sediment responses, coastal sediment trafficability, geotechnical aspects of coastal erosion, and geotechnical reconnaissance after coastal extreme events. Dr. Stark has received both the Career Award from the National Science Foundation and the Young Investigator Award from the Office of Naval Research, and she earned her master's degree in geophysics and her doctoral degree in marine geotechnics, both from Germany. Nina, please proceed.
Thank you, Rula. Thanks for the very kind introduction. Thank you for this opportunity to present in this webinar series. I'm really excited and feel very honored to have this opportunity to present my work to the audience here. Okay, so just to provide a quick overview of what my presentation will be about today. So I will talk first about the motivation of this work and geotechnical characterization of subaquatic environments and the specific project goals. I will then introduce portable freefall penetrometers, which is the type of instruments that we are proposing and investigating here mainly, as well as current data analysis strategies for these devices. Then I will present some of the advances and proposed changes in the data analysis framework that resulted from our research here. And I will show results from a field demonstration before finishing with some conclusions and comments on the benefits to DoD. Please note that I list the literature associated with the presentation and the additional resources for your availability. So geomechanical properties of seafloor surface sediments describe the response of seafloor sediments as a bulk material to different stresses, loads, and other interactions. So we are looking in geotechnical engineering at the sediments as one bulk material and how they're responding, how they're arranged in the seabed. So not necessarily only at the particle level of the sediment. Such properties affect the characterization, assessment, and management of submerged munition sites in multiple aspects. The sketch here depicts some of them. So the water column is here shown in blue, and the seabed sediment is shown in brown colors with different layers of different geomechanical properties indicated by these different shades. So we are assuming in this example that a top layer exists that is a little bit softer and or looser, and that there's a bottom layer that has different properties, and here we are assuming that it's a little bit harder or denser. So more specifically, this can then lead to, for example, an increased burial depth. So if we would be misinterpreting this surface layer, for example, assuming that it has the same strength as the underlying material, then we could actually have a deeper burial depth of an object here. There may also be a higher risk of exposure or burial by sediment dynamics if we don't really get the characterization right here. And even we may want to think about like ambiguity for acoustic or optic surveying results if we actually do not characterize the sediment here correctly. So traditional geotechnical seabed testing includes larger cone penetration testing rigs, as shown here in the left image, or sediment coring and subsequent laboratory tested, what is indicated by the center and right image here. Those methods can be quite time and cost intensive, and they may also suffer from limitations in applicability from environmental conditions. Such conditions could be energetic hydrodynamics or delicate habitats and others. So you can imagine if you're looking at the CPT rig here on the left, that you may encounter issues that you cannot deploy it under certain wave conditions or current conditions, or you could envision that you're in a very delicate environment, that this whole frame and needing a larger infrastructure for this could represent an issue. So this may then lead to actually a decrease in spatial as well as temporal coverage of measurements. So if it's a lot of effort to get these measurements, you may take less of those, or it may take longer to actually get there and do these measurements if you are in more urgent data needs. And so this can also lead to impacts on your certainty or accuracy of the characterization if you are left with less deployment locations. Freefall penetrometers, and specifically portable freefall penetrometers, have been introduced to fill this gap mostly over the last decades. So the idea here is to have devices that require less infrastructure, so they may be able to be deployed even without a winch, so you need less of a larger vessel here. And we are typically referring to freefall penetrometers when the instrumented cone penetrometer is inserted into the seabed by self-weight and momentum instead of driven by a hydraulic reaction frame. So if you remember the picture from the previous slide, you have this, this rig where you have your hydraulics in there to push the cone in at a certain velocity. In this case, we're practically utilizing weight and the free fall through the water column. The left image actually shows a short version of a free fall penetrometer that carries otherwise the same sensor suite traditional cone penetration testing offers. While portable freefall penetrometers are a little bit lighter traditionally and short enough to be deployed by hand and without a winch or other infrastructure. So that makes them a little bit quicker in deployment, and that makes them also suitable to access areas that may otherwise not be really accessible with larger vessels. Examples of portable freefall penetrometers are here shown in the images from the second left to the right. While portable freefall penetrometers have clear advantages regarding the deployment, they often carry a lighter sensor suite, so not the same sensors as traditional cone penetration testing would. So the traditional cone penetration testing would carry a tip resistance sensor, a sleeve friction sensor, and usually pore pressure measurements. However, you can imagine if you have a tip resistance sensor, the device is also more susceptible to damage, particularly if you're in areas of fairly unknown conditions. While portable freefall penetrometers, if they do not feature like a tip-resistant sensors, but are more based on, for example, extrometers, and I will get to that a little bit more in a second. Then they're practically constructed that they have massive steel tips and therefore are actually more rugged in case of the seabed conditions are unknown. However, with less sensors, and in particular differently than traditional sensors available, that also makes the data analysis a little bit more complex. And in fact, this is still the subject to research, including studies like the one that I'm presenting here. So in line with the gaps in knowledge related to data analysis and then also the application for munition response in subaquatic environments, our project goals were first to investigate the variability of geomechanical properties in subaquatic environments. So we are interested in how much differences are we actually seeing in these geomechanical properties, and I will come to which properties I'm talking about in a second, and how relevant is that? So we also want to understand and investigate how much do these variations affect actually the things we are concerned about when it comes to subaquatic unexploded ordnance sites. So for that, and for using devices that allow to do a lot of measurements to really look at that in detail, we have to assess portable freefall penetrometer performance specifically for this purpose a little bit more in detail. And then it's also something that we identified that we are running currently, or I should actually now say, more so in the past, into the issue that there were a lot of different suggestions how to analyze the data. However, there was not a really well streamlined procedure that would make it very accessible to actually get a consistent results here. So let's talk a little bit more about portable freefall penetrometers. And in this case, we utilized this approximately projectile-shaped probe that you see here on the right side. So there are some advantages of the shape. So if we are having a little bit of a tapered main body towards the tail, we are actually avoiding that we get a lot of effects on our motion of the penetrometer from side friction on the shaft. So we sometimes also refer to full flow penetrometers when the tip is actually wider than the shaft or the body behind it. So here I'm always a little bit reluctant about doing that because traditional full flow penetrometers would have usually a significantly wider tip or nose and then the shaft. However, here we found that this is just enough to avoid that we have significant shaft friction effects. What is important for us, because most of the resistance that actually brings the penetrometer to a stop or changes the motion of the penetrometer in the sediment is really focused on the tip. So just as a reminder, differently than in cone penetration testing, we do not carry a sleeve friction sensor here. So we do not measure the friction on the shaft, and therefore it's good for us that we can avoid this with a slightly tapered tail here. We have, in this case, in the images, you see it with a conical nose. However, we also have a hemispherical, or I should actually say hemiparabola nose available, what we use specifically for very, very soft sediments where we, through the shape, can actually improve the accuracy on the resistance here. This probe is actually suitable for water depths up to 200 meters. However, I will admit that it's very rarely that we use it to these depths. And it's also getting more difficult because you have to think then about rope drag, because then your rope may actually slow down your penetrometer and free fall more and more. So in case we go deeper than 100 meters of water depth to deploy these, we have to be very careful about the rope we are using. The device is very robust. It has survived many times impacts into rocks, other unknown hard objects on the seabed. It has impacted seabed fast and ice before without significant damage other than some scratches on the cone nose. And this is specifically of interest if we're not really sure about the seabed conditions prior to deployment. And it's also convenient if we are dealing with difficult conditions, like, for example, energetic hydrodynamics, where maybe the probe may also shift a little bit. The deployment is very fast. It falls typically with velocities of 4 to 6 meters per second through the water column. So you can imagine, depending on what your water depth is, your deployment may be less than a minute, and including bringing it back up. And then often, because it is so fast, we actually deploy it 2 or 3 times in the same location to also assess actually how much small scale spatial variability we have here. It's very lightweight. You see here a photo where I'm actually holding it. It's about 8 kilograms. So that means I would not necessarily want to hold it like that for a very long time. However, in water, it's fairly easy to pull up by hand. So that makes it, again, very convenient to practically deploy from any vessels of opportunities. Penetration depths are typical up to 30 centimeters in sand and up to 300 centimeters in muddy sediments. So penetration depth is clearly a limitation of freefall penetrators, and particularly portable freefall penetrometers that are not very heavy. So compared to traditional cone penetration testing, where you would use a hydraulic jack to actually get to the desired penetration depth, or even thinking about a large-scale freefall penetrometer that can be made very heavy potentially, here our penetration depths are limited. So here I want to say very clearly, if you have a project or like an interest in geotechnical properties, meters down into the seabed, then devices like this are certainly not very useful. However, if you're interested particularly in the top 2 meters, this could be potentially a really quick and fairly efficient instrument for you. It measures, this instrument specifically measures its own acceleration using actually 5 different accelerometers, and then it has also a 3D accelerometer to measure potential tilt. Overall, it falls very straight, but it can happen on sloped seabed surfaces that it may tilt or slip a little bit to the side. So for that, we have an inclinometer or like a multiple direction accelerometer so that we can assess that and then react accordingly in the data processing. The different accelerometers have the advantage that they are in different ranges, because if we are impacting, for example, in soft muds, we are usually encountering a deceleration in the range of only 2 Gs. So it means we want to go to a fairly low range, high accuracy accelerometer. While if we are impacting a sand, it's not uncommon that we can reach up to 100 or more Gs of impact. And then obviously we need a little higher range accelerometer here. So we're trying to use multiple accelerometers to practically get the best of both worlds, getting a wide range, but also highest accuracy for the specific range. This penetrometer also carries a pore pressure sensor that is located in what in cone penetration testing is typically referred to in the U2 position, what means that it's actually behind the nose cone. And you see that in the upper right schematic indicated by this little blue box saying porous ring. So here you have a pore pressure sensor, and that is fairly unique. Not many portable freefall penetrometers carry a pore pressure sensor yet. I will come to that a little bit later, why so far people have stood back a little bit from this. There has been not that much experience on interpreting pore pressure results from these high velocity impacts. However, they actually turn out very useful, and we have been starting using them more and more. Okay, after having talked about portable freefall penetrometers, let me introduce some of the main approaches for data analysis for these devices. The most direct interpretation of the data is to conduct a seabed classification directly from the measured deceleration. So in the left figure, you see an example by Bob Stoll and colleagues developed for a similar probe called the expandable bottom penetrometer. The figure displays measured deceleration versus time, and a time of 0 indicates here the impact with a seabed. This is also reflected in that there's no acceleration or deceleration prior to impact, meaning that the probe is actually moving approximately with terminal velocity of the free fall through the water column. The different curves here represent independent deployments, and you can see that it was proposed here to classify based on the maximum deceleration the seabed into 3 groups. one group of impacts reaching less than 20 G, one group reaching more than 60 G, and then a group in between marking a soft, hard, or intermediate seabed respectively. As the direct data output is used here, this classification is extremely rapid and can be practically read out immediately. In the center plot, you see results that Thomas Wefer and myself published, data from actually the same probe, also expandable bottom penetrometer. And here we looked actually at the deceleration profiles a little bit more in detail instead of just looking at the maximum deceleration here. So in this case, you see the deceleration again on the y-axis, but now you see the penetration depth on the x-axis here. And you see a profile where we knew from core samples that we have two different types of sediment. So we have in the upper 15 centimeters mud indicated by the orange shading, and then at the deeper depth, so in this case, the penetration depth was limited to about 25 centimeters. And you see that then we have a silt starting from about 15 centimeters. Again, this mud-silt distinction was actually determined from core samples. But you see very clearly that in the deceleration curve of the probe, you have two very different gradients for the zone of the mud and the silt, and it just fits really perfectly also with the core classification here. So going practically from what is shown in the left graph, we went a little further and said, hey, there's more in there than just using the maximum deceleration and practically categorizing the seabed in this penetration depth generally in soft, medium, and hard, but we can actually see that different sediment types are reflected differently in the gradients and in the penetration profiles with depth. In the right figure, you see deceleration depth profiles, and I apologize that here the axes are flipped, so please pay attention now. The deceleration is actually on the x-axis, and you have penetration depth on the y-axis. Again, 0 indicates here the water seabed interface, so practically 0 means we are hitting the seabed, and then we are reaching, in this case, penetration depth just about over 40 centimeters. So this was actually measured with the same probe that I will be focusing on in this presentation. You see 4 deployments along a cross-shore directed transect in the nearshore zone of Collinson Head, that's near Herschel Island, in the southern Beaufort Sea. And here the directly measured deceleration profiles are used to indicate variations in sediment strength and therefore geomechanical properties of the seabed from closest to the shore, being here the black line. You see you have very little penetration depth and immediately a fairly strong deceleration indicating very hard sediments. And then the further you go offshore, you immediately see that it's getting softer, your penetration depth goes deeper, and your deceleration goes further down, indicating clearly the change from harder sediments to softer sediments along this cross-shore transect. So again, taking it practically a step further and using this to compare different profiles along certain spatial distributions. So we can already obtain information from the directly measured results, but the deceleration is not really a geomechanical property that we could easily implement in further interpretation, other than giving this qualitative perspective of sediment strength and change in sediment. So how do we get here to geomechanical properties? From our deceleration measurements, we can utilize our knowledge of the probe's mass and dimensions, as well as consider other possible forces such as soil drag and buoyancy, which I will address in more detail later, to estimate a sediment resistant force. So this is the force that practically decelerates the probe, slows it down from the impact velocity, and brings it eventually to a stop. And we can just utilize simple Newton's laws to get from practically our motion to our sediment resistance force. We also know the dimensions and the loaded surface area, what allows us to convert this force into a load, or in this case, we tend to refer to the dynamic bearing capacity. We can think of these vertical soil profiles as an infinite number of layers of certain bearing capacity layers, and each layer fails as long as the penetrometer advances. So that means by breaking through, we're measuring the maximum resistance for this layer, means we're getting an estimate of this bearing capacity. However, our penetration is non-static, what means in this field that we are actually changing the penetration depth. So our velocity changes throughout the penetration. If we're thinking back at more standard geotechnical testing, such as cone penetration testing, there the penetration is at a constant velocity. And to highlight this, we refer here to the dynamic bearing capacity, because we know that soils can exhibit a different shear strength if you shear or load it at different velocities. To just think about it, you would have a layer or like a bin of mud, and you would poke the mud really, really slowly and will feel really soft. But now imagine you would try to do this very fast with a high impact, and you will feel much more resistant, and maybe your hand will actually hurt. So this is exactly what I'm referring to, that depending on how quickly you impact, how fast you're straining your soil, you will get a different strength response. This is obviously a problem if we want to compare our results. So to compensate for this and derive a bearing capacity that is comparable to other testing methods, we need to apply a strain rate correction to derive the so-called quasi-static bearing capacity. So it means we know that it's not really a static penetration, but we are normalizing our measurement to a constant penetration velocity, what is typically 2 centimeters per second in line with cone penetration testing. And then it should be noted here that this strain rate normalization actually relies on empirical strain rate factors, which are sediment type dependent. To derive a widely used geomechanical expression of sediment strength, such as undrained shear strength for muddy sediments or friction angle for cohesionless sediments, we may then need to apply a cone factor or may need to know the relative density. And I will talk about this a little bit more later. So in cone penetration testing, the use of pore pressure measurements is well established. But as I mentioned before, very few portable freefall penetrometers feature pore pressure sensors. Additionally, even for larger freefall penetrometers, pore pressures have not been that well investigated. Therefore, this aspect is still quite new, particularly again for portable freefall penetrometers. And let me just explain how this actually works and why it may be valuable. So the pore water reflects hydrostatic pressure unless a significant presence of gas or some other conditions at the sediment, but for many cases you may validly assume that your pore water reflects hydrostatic pressure. However, as soon as the penetrometer starts pushing into the sediment, pore pressures may increase from squeezing of the pore water when the soil is pushed out of the way of the penetrometer, and hydraulic conductivity prohibits a rapid diffusion of the build-up pressure through the soil, or pore pressure may actually decrease from rapid soil loading through dilation, if the sediment is dilating, what's mostly typical for sand. This means that we should expect that we can observe a pore pressure response through a recording of the penetrometer that reflects the soil properties as an actually independent measurement, other than dependence on the velocity, in addition to the previously described analysis of the deceleration. So the figure here shows 2 examples on the upper and lower panels respectively. So you see on the left side the deceleration curves, and if you look at them, you see again different gradients, and it's also highlighted here through the different shading. So from the deceleration measurement, it appears that we have 3 different soil layers here, with the one in blue indicated here with almost no resistance to the penetrometer, then an increasing resistance to the red layer, and then even more through the green layer, and then even more resistance to the red layer. If we're now looking at the center panel, that is actually the measured pressure, and you see as this dotted line that I hope it appears as dotted, otherwise a more grayish line. That is the hydrostatic pressure as it is predicted based on the penetration depth. And you see that, for example, in the blue sediment layer on top, it follows hydrostatic pressure really nicely. While if you're entering the green layer, you see more of a, certainly first, subhydrostatic behavior. So you're actually seeing less pressure than you would expect. While if you're then entering the red layer, you see that the pressure is going up again in case of the lower profile just reaching hydrostatic pressure, in case of the upper case actually going towards a significant excess pore pressure. On the right panel, you see the excess pore pressure, so that means the difference to hydrostatic pressure, also shown as a separate plot. So that means we see these different sediment types also in the pore pressure, what makes it really attractive, because maybe we can get practically two measurements with one deployment that both help us unravel the sediment conditions here. So from these considerations of existing data analysis methods, we came up with this idea here of one unified framework to just work through if you only have the portable freefall penetrometer data and maybe some general soil information from other data. So we are proposing to leverage the raw measurements to distinguish between cohesive and non-cohesive sediments, then follow and advance existing approaches to derive the key geomechanical properties such as friction angle and relative density for sands. So this is indicated here on the left branch of this flow chart, considering shearing behavior as well as in situ texture. And then underlying shear strength and the coefficient of consolidation for cohesive sediments, following here the right branch here, where we again first are determining that we have cohesive sediments, then we may determine that they're in the range of normally to over-consolidated muds, or maybe they're in the range of very soft muds with really high water contents, and I will come to that a little bit later. And then we have also identified this aspect of what if we have really a lot of organics and bioturbated muds, and also just a lot of benthic biogenic processes, and I will talk about this a little bit more later. So first, we looked into if we could use the penetration depth that is derived from the distillation time record directly to distinguish between cohesive and non-cohesive sediments. So as this first step in this framework that I just showed in the flow chart. So we found that shallow penetrations reaching less than 20 centimeters were mostly restricted to sands, with in most cases, in fact, significantly less than 20% of fines. So in most cases, it was actually even less than 5% of fines. If the penetrometer reached more than 25 centimeters of penetration depth, and just as a reminder, this is for the probe that we investigated here, these specific values may have to be recalibrated if the probe is being changed, then we saw that literally all sites that we tested this were actually sediments with cohesive, with high cohesion and more than 20% fines. And even for the sites with penetration depth of 20 to 25 centimeters, most of the sediments featured more than 20% fines. This concept idea is very similar to Stoll's use of maximum deceleration that I presented earlier, as well as Molekutler's firmness factor that I did not present here in more detail on, but that utilizes penetration depth, maximum deceleration, and impact velocity to distinguish between different sediment groups. However, here we are only using this to inform which subsequent data processing method should be applied. More specifically, this suggests that we attempt a sand-based data processing if our penetration depths are less than 20 centimeters, and with fairly high confidence, we should apply a cohesive sediment data processing method if penetration depths are larger than 20 centimeters. So as a key takeaway, the sediment type as relevant for further processing and soil behavior can be determined with fairly high confidence from the deceleration record directly. The calibration, again, would need to be adapted if changes of the probe would occur. Let's assume we find non-cohesive sediments first. So this means for most areas of interest, sand and maybe fine gravel. In initial freefall penetrometer studies in the 70s and 80s, it was believed that penetration velocity can in fact be neglected in sandy sediments. Just as a reminder, we are penetrating with velocities magnitudes higher than standard geotechnical tests. Just as a reminder, standard cone penetration testing at 2 centimeters per second, we are talking here typically about 4 to 6 meters per second. However, within the last decade, there has been strong consensus that actually viscosity effects drive a dependence of the measured sediment resistance on penetration velocity, even for sandy sediments. Specifically, Chow et al. And White et al. Proposed that the use of backbone curves as shown here to account for this. Those authors demonstrated the validity through theoretical and controlled laboratory testing. Here, this figure is one of ours where we tried it out in the field. So what you're seeing here, on the x-axis is the dimensionless velocity. This is the penetration velocity times penetrometer diameter over the horizontal coefficient of consolidation. So for a dimensionless velocity smaller than 0.1, we are expecting a drain behavior, meaning the pore fluid is allowed to drain and equilibrate during the penetration. For large dimensionless velocities, we expect an undrained behavior where none of the pore fluid can escape fast enough, and in between, we expect partial drainage. Each curve then represents a certain relative density of the soil, being the state of the sediment between its loosest or densest packing state. For a certain relative density, you can follow then the sediment resistance and how the sediment resistance would change for different penetration velocities, with strength decreasing with an increase of velocity for very loose samples, however, increasing for very dense samples. So if we would just choose here, for example, a relative density fairly low, let's put it here at 10%, and we would start with an actually really high velocity in the undrained zone, we would have here, would measure maybe a strength in this range here, dynamic strength here. If we would want to normalize it to a slow velocity, maybe even in the drained range, we would in this case actually measure or expect a higher strength. So we have to account for that. Interestingly, if we have denser samples, so going here up to some of the higher curves, we would see something practically vice versa. So if we would start again with high velocities and we want to normalize it down to a smaller velocity, we may actually decrease here in strength. So you can see that there are some relative densities where in fact velocity effects are fairly minor. However, there's also others where the penetration velocity is quite important for the sand here. So how do we know what the relative density is? Because that is in fact really a pain to get for field workers. If you're thinking about getting a sand sample that is so well preserved that you have all the in situ texture, all the particles are where they were before and where they are in the seabed. So we could try to get these high quality sediment samples that preserve the in situ texture of the sediment, but this is very difficult in most sandy seabed sediments. Instead, we tested here the hypothesis if we know that the seabed is governed by a certain sediment type, in this case sand, and also a certain sand in a specific grain size range, then we assume that the change in strength and resistance would mostly actually be governed by the packing density or the relative density. So we asked this question, could we relate or calibrate the deceleration directly to relative density here? And indeed, we established this curve here in the laboratory where we could control the relative density for medium nearshore sand, and we got a really good agreement in this calibration between the deceleration and the relative density. Again, if our sediment or specifically the sand type would change more specifically, you would have to recalibrate this potentially. Again, knowing that we are on sand, we can follow now a theoretical bearing capacity approach or utilize actually available empirical correlations that have been published in geotechnical engineering that relate the relative density and the measured bearing strength for the desired velocity. Keep in mind, again, we are aiming usually at 2 centimeters per second to be in line with standard geotechnical testing to derive a friction angle. In the figure, you see a comparison of the friction angle derived this way from portable freefall penetrometers, here indicated as equation 9. I apologize, this is a figure from a paper that we published. So you see here on the y-axis practically the estimate from the penetrometer with the method that I just described. And then you see on the x-axis results from standard triaxial shear testing in the laboratory. And I feel confident and good about saying that this is actually an excellent match. So to sum up here for the sense, so indeed, we were able to show that theoretical as well as empirical approaches can be applied to portable freefall penetrometer results to derive friction angles as well as relative density of sandy sediments. Those properties are relevant to predict and assess the seabed response to, for example, an impact of an object, but also to predict erodibility, susceptibility to liquefaction, as well as porosity relevant for geoacoustic purposes. And with that, I will actually stop here and we will have our first quick Q&A session. Thank you.
Thanks a lot, Nina. We've received a number of questions, and just as a reminder for those of you that are still getting the questions in, please use the Q&A box on your screen, not the chat box, to submit those questions. So we'll take maybe 3 to 4 questions, Nina, starting with one from NAFAC Southwest. You mentioned that the portable freefall penetrometers are pulled up by hand. Do you have to utilize divers for the retrieval? Can you elaborate on the retrieval, please?
Sure. So we attach a rope to the tail, and so we can be pretty picky on the rope. So we try to take thin ropes that are thin enough that we don't get significant slowdowns to the water column thanks to rope drag, but thick enough that it doesn't make it too uncomfortable for whoever is handling the penetrometer. So for example, in deeper water, where we were really concerned about drag, we have used Kevlar lines, and we practically used fishing lines to pull it back up. So there's a rope attached. We have used also practically capstans to bring it back up to help, in particular in deep water, and a davit and a block, for example, to help. But so the main concept is you have a rope attached. We are trying to optimize the rope to have as little impact as possible on the free fall from the rope, and then we just pull it up on the rope. So no need for divers.
Great, thank you. And this next question is from Jacob. Engineering, what is the depth at which the penetrometers achieve terminal velocity?
Yeah, that's also a really interesting question. So because we actually do have a rope attached, we never reach truly a terminal velocity. So we are getting really close to a terminal velocity after about 3 or 4 meters of water depth. However, as we are actually correcting for the velocity as it is, we don't really need to reach the terminal velocity. We can handle practically the dynamic velocity range in the data processing. So, and because we have the rope attached, you're practically accelerating through the water column, and then you very, very slowly actually see with more and more rope going out, the velocity slowing down a little bit from the rope. Again, this is also then depending a lot on what type of rope you're using. But so to be quite like honest here, we never really reached a perfect terminal velocity, but we are accounting for that in the correction when we are correcting for the penetration velocity.
Great, thank you so much, Nina. This next question is from Penn State. Where exactly is the pore pressure sensor located on these devices? Yeah. And do they measure static pressure or dynamic pressure?
Yeah, so the pore pressure sensor is in practically centrally on the axis of the probe directed forward, and is connected to the outside through little canals. And then we have actually a filtering that goes around it. So that is actually also, like, from the deployment perspective, currently one of the hardest aspects. So we have to make sure that this is all very well saturated. We have a little inlet where we can inject a saturation fluid. We usually use actually a mineral oil for this, so that we have a bit more viscosity, so it doesn't get sucked out of the filtering during the free fall in the water. And so we are saturating practically the whole pore pressure system prior to deployment. And so we have, I think for this probe, 4 or 5 canals that actually come out and allow the connection to the filtering and then to the surrounding water. And so we measure, in this case, the pressure throughout the fall. We have then to correct for some fluid dynamics effects, and then again during the penetration.
Wonderful. And maybe one last question, and we promise
Sure.
to get back to the remaining questions towards the end. This next one is from NYU. How confident are you that the bearing stress coefficient is not influenced by the friction on flanks and fins?
So on the friction on the sleeve, did I understand the question right, Rula?
It's not specified. It says by
Okay.
friction on flanks and fins.
Okay, yes. So the fins are a little bit narrower than the maximum diameter. And again, the tail is tapered off. So I would agree that if we're on sticky clays, there's probably some effects of adhesion. And we have actually also looked at that a little bit for sticky clays. Otherwise, in some lab experiments, we have seen that we actually maintain a little film of water. So the opening of the penetrometer is actually usually maintained as wide as the penetrometer is. And also in comparison, where we had the chance to compare to other penetrometers, it seems that indeed most of the resistance is centered against the probe. However, again, if we have very sticky sediments and also very soft ones that may collapse, in particular around the penetrometer when it advances, there can be some effects here. But we feel that they're more minor, but it's also something we are still looking into a little bit.
Great, thank you. All right, well, let's go ahead and have you finish your presentation, and we'll get back to the remaining questions, and let's try and target 25 minutes for you to conclude. Thank you so much, Nina. Please proceed.
Excellent. Thank you, Rula. And thank you, everyone, for the questions. Really great questions. So let's now move over to cohesive sediments. And so penetration depths are here significantly deeper. So questions also arise here regarding drag and buoyancy and how they affect the measurements. So we are accounting for drag and buoyancy of the seawater, but what if we consider a soft clay exhibiting a high viscosity fluid behavior, and how much does that potentially affect our results versus a more traditional tip-bearing resistance? So this has specifically been previously proposed for the uppermost centimeters of the seabed. So we looked into this issue a little bit more here in detail. So what you're seeing here is the top 8 centimeters of a penetration for a purely fine-grained sediment side on the left, so that's the clay bank and the York River, then a purely sandy side on the right, so that's around Goodwin Islands, also at the York River mouth, and then a more mixed sediment side in between here named Naval Weapons side, what is also located in the York River. So the solid black line shows the measured sediment resistance force. The red line indicates the calculated contribution of soil buoyancy based on bulk density that was determined from high quality sediment samples. And then the dashed line suggests the calculated contribution from soil drag. And this is again based on the bulk density from the sediment samples, our knowledge of penetration velocity, and the drag coefficient that we worked with for now from knowledge of torpedo anchors and other penetrators. So we see that the effects of soil buoyancy is pretty small, as was expected, but the drag can actually have a major impact here in the top 8 centimeters. Specifically for the more clayey sediments, you see that in case of the Goodwin Island side on the right, the measured curve is taking off actually after about 4 centimeters, really beyond what the drag would suggest. However, for the clayey side, the clay bank, we see that there is some additional increase in strength that cannot be explained only by drag and soil buoyancy starting here at these 8 centimeters. But then we also actually see that for naval weapons, interestingly, we have here quite some overlap. So this is something we are looking more into, and in particular also discussing with a lot of colleagues from soil mechanics, and I'll come to that a little bit more in a second when we talk about very soft sediments. So how are we really dealing with these soft surface sediments? Because traditionally in geotechnical engineering, very often we have this argument, okay, we don't really care for these top 8 centimeters or 10 centimeters, because for a lot of the traditional geotechnical problems, they are not very relevant. However, for a lot of the problems we are looking here, particularly when it comes to erosion and erodibility, they are becoming quite important. So similarly, as previously mentioned for the sands, and even more so for the fine-grained sediments, we do expect that the soil exhibits a strain rate dependence. So again, that we are seeing that the resistance of the soil changes depending on how fast we try to shear or displace or push through it. So that means that there's a change in strength depending on the velocity. And so literature suggests either a logarithmic or an inverse hyperbolic sign or a power law relationship to normalize the tip-bearing resistance from an actual penetration velocity to a constant and standard velocity. So again, we're usually going for these 2 centimeters per second. So those formulas, however, include a sediment-dependent empirical factor. This is indicated here in the left plot, where we are showing like a logarithmic expression to this K factor. And then on the right plot, you see practically the same profile, and then applied as this power law strain rate correction with this beta sediment factor. So this figure demonstrates how much actually your result changes depending on the sediment dependent factor. So if we're looking here at these different curves with color, so the red one, so the very much to the right, the highest value is actually a very, very small strain rate correction, right? And we're applying more and more strain rate correction going to the left to these cooler colors here. But if you're looking at the values, that's quite a significant difference in value. And that puts us somewhat into a dilemma because we are actually having to decide what factor we're using while we don't really know the sediment yet, right? So how are we choosing this sediment dependent factor if we're not really sure yet what is the sediment and we're trying to characterize the sediment? So additionally, we also have to apply another empirical factor to actually get to undrained shear strength. And in this case, this is, we are also referring similarly from cone penetration testing to a cone factor to then get from our quasi-static bearing capacity to an undrained shear strength. So we were able, in this study, we went to a lot of different sites with different sediment types. We collected high quality samples. We processed these samples in the laboratory for the undrained shear strength values. And then we looked at the comparison at the results, and we actually calibrated these factors here. And we were able to practically identify 3 groups of general fine-grained sediment type behavior that lead then to favorable matches within ranges that are actually considered or have been shown previously in the literature. So we were quite happy that that's consistent with people, what have people observed before. However, it should also be noted that that if we're just looking at CPT calibration or cone factors, for example, that very little CPT calibration has been conducted really for these surface sediments. So that means we always have to apply some caution here. So here you see some results where we are looking at certain cone factors apply, and they're very well in the range what you would also potentially apply to CPTs, and compare them to laboratory tests for these 5 different sites here. And you can see that you are actually reaching a quite favorable match between, in this case, these are mostly vein shear tests indicated through these black dots with our penetrometer estimates shown as the black line here. And however, you may also notice that the match is kind of diverting a little bit if the sediments are actually really soft. So particularly surface sediments, often like less than 2 kilopascals or 1.5 kilopascals. And I will come to that actually in a second again. But so this was for us a very satisfying result, seeing that we can actually produce with our penetrometer with the calibrations that we found, and we suggested based again on the initial profile characterization from deceleration curves, a certain fit to standard methods. So just to wrap that up as a summary, so the undrained shear strength of cohesive sediments can be indeed determined with quite acceptable confidence. However, uncertainty can arise from these very soft sediments and various impacts on seabed surface conditions, what could also be, for example, benthic biogenic processes. So before I get to very soft sediments, I just want to talk about pore pressure dissipation tests a little bit. So I've shown pore pressure results during the penetration before. However, in cone penetration testing, pore pressure dissipation tests are also being performed to look at the state of consolidation of the sediments. In this case, for the dissipation test, what we're doing, we're deploying the probe as we always do. However, we actually leave it then in place for quite a while. And then we monitor how the pore pressure, the excess pore pressure beyond the hydrostatic pressure, diffuses or dissipates with time. So here you see two examples where we reach pore pressures well above the hydrostatic pressure during penetration. So you see that how the black line goes well above this dashed hydrostatic pressure line. And then we see that with time, this really, really slow decay of the curve. And you see that it takes quite some time to actually get here a significant trend. So in this case, measurements have been conducted over an hour, but as you can see from these curves, you would need probably at least 20 to 30 minutes to get a meaningful result. So if you have these curves, we actually tried out to apply a similar approach as has been done for cone penetration testing. So we're looking at the T50, so that is actually the time to diffuse 50% of the excess pore pressure, and derive from that the coefficient of horizontal consolidation. And here are some examples how we did that. I provided at the end of the slides the reference for this, where we have all the details in the paper. However, to just move forward here, we were very pleased that we could actually get a realistic result of the coefficient of consolidation, and that the pore pressure dissipation test can indeed provide these relevant complementary information. However, these tests are fairly time consuming, and they require also some special attention during deployment, mostly related to what I responded to in one of the questions during the question round regarding having a good saturation of the pore pressure filtering, because these results get very heavily impacted if there's gas in this pore pressure measuring system. Then I want to also talk about, as I mentioned before, these very soft cohesive sediments. And I will admit that particularly in this study, we really started paying more attention to this, because we noticed we achieve these really good fits overall as soon as we are past some of these very soft surface sediments. So on the right, you see an example of a core sample with such really fluffy sediments. I tend to compare them to cream. If you move your hand through them, they practically feel like cream. And there's a number of challenges with these sediments. So for example, the water contents are well beyond the liquid limit. So it means if you're testing these sediments, they exhibit actually no plastic or elastic behavior, but actually rather a liquid behavior. So it may be questioned, should this be really treated with soil behavior or soil mechanics concepts? It is also really difficult to sample this material, as it tends to escape while bringing it up, or it just flows out of your core tube. Or even if you succeed in bringing up the sample successfully, there's still this consideration that this sample consolidates really quickly during storage while trying to get it to the laboratory. And then also a lot of the traditional geotechnical methods actually lack this sensitivity for such soft sediments. And finally, again, you may ask, okay, is soil mechanics really the right approach, or should we look actually more at rheology, for example? And here's just an example for that. So we have here the undrained shear strength as the solid line as estimated from the Freefall penetrometer, and then compared again to these laboratory vein shear results here with a cone factor of 12. So we get here in this case a pretty good match beyond 50 centimeters of penetration depth. And then our results are slightly diverting higher up. But I would also like to point out that the difference is really, really small, and in many cases less than a kilopascal or half a kilopascal. However, because we are in these really soft sediments, it actually represents potentially a quite decent amount of the actual strength. So we see here in the water content measurements that we're actually really well beyond the liquid limit here, again pointing at that this is not really behaving much as a soil, in fact. So if we're looking at this a little bit more, then we could think about, we have these three zones, right? We have this top zone where we actually attempted to get like laboratory data, even with a vein shear, what is like a method that we prefer for very, very soft sediments. But our Venture was not even able to measure anything there. It practically just measured zero resistance because our springs, we didn't have one single spring that was able to really get an accurate measurement of this very soft surface stuff. But we can see this in the penetrometer, so that is actually exciting that we can resolve this. But then we have this zone in between where we have vein shear measurements, but they don't match really the freefall penetrometer. And then we have the zone where we get this good match. So we are asking here, should we actually treat the surface maybe more from a perspective of rheology? And we have started doing that, collaborating with a colleague at Virginia Tech who conducted some rheology tests on the material, and seems that that actually fit really well. And then we have the soil behavior further down where we, with our standard approaches, get a really good match here. However, then we are in this zone in between, and so what are we doing there? And that is really still also a subject to research. How are we dealing with like profiles like that, where we have this very soft material on top? And so we are maybe transitioning from rheology to soil behavior, but then we have this transitional zone, and what are we doing with that? So the geomechanical behavior of very soft seabed surface sediments may be described in rheological or geotechnical terms. And then seabed sediments showing a transitional behavior will, however, require some more research in our perspective. So I talked a lot about these different geomechanical properties like friction angle, relative density, undrained shear strength, and coefficient of consolidation. Now let's relate that quickly back to what we feel this may actually assist with. So friction angle affects erodibility, but it also affects the modeling of impact response, particularly in non-cohesive sediments. Relative density, important also for erodibility, impact response, the risk of seabed liquefaction, but also for geoacoustic properties because it's practically also an expression of porosity. Then undrained shear strength, important potentially and related to erodibility, geoacoustic properties, impact response for sure, but also a slow sinking through consolidation of objects, right? In particular, these very soft sediments may start consolidating under an object, and then the object may slowly sink in. And then, of course, the coefficient of consolidation is then even more important for the sinking, but also for potential risk of seabed liquefaction, erodibility, as well as geoacoustic properties. While we have made these first steps towards showing these direct applications, this is still work in progress, and I will get to this a little bit more soon. But in this project, I would like to next talk about our field demonstration to test if we can actually confidently derive these properties in a new area and in a rapid fashion. So all the data I presented before were practically gathered in sites where we collected samples, where we did the freefall penetrometer deployments, and then we really looked at the data in detail. So what we tried here, we went to the Potomac, and we did practically a grid. You see these different data points labeled, the round circles, and we actually dropped the penetrometer there without knowing much about the seabed other than an approximate depth and therefore bathymetry. So from the results, just from the penetrometers where we collected the data, it took, I think, 2 or 3 hours to drop multiple times in each of these dotted locations. We went then back, in fact, not to the lab, but actually to a hotel in our laptops. We did rapid processing using the methods that I had just demonstrated and explained. And so we came up with these 4 main groups where we also split group 4 up a little bit, but practically we were able to get the whole area into 4 groups of distinct and different geomechanic profiles that we determined. And they looked about like this. So you have here on the top left, the group 1, these are all of these curves are independent deployments. So they're not connected, they're not all at the same size, they're actually at these different dots. But you can see we have a very consistent behavior with quite significant penetration depth. Then you see on the right side, less curves here, less data points, smaller group here, but significantly different behavior, right? So you're still in the same range, reaching just about 2 kilopascals, but clearly there's a different going on in the surface. So while on the left side, the profiles, you have more this consistent increase, you have here on the right side, a really like stiff or maybe hard surface. This could be, for example, also shell or gravel or something a little bit coarser deployed here. it creates a first big resistance, and then we are going more into a consistent, softer profile. And then on the bottom, you see more variation. However, they have also some things in common where you have these top 8 centimeters of like a little bit softer or less strength. And then after 8 to 10 centimeters, it clearly increases in strength. And overall, the strength is actually larger here. So, and again, just as a reminder, this was very rapidly processed, practically on-site, on laptops that you're carrying out in the field. And so we were able to classify this material very rapidly. And what we did then is we went back, collected core samples, and compared this. And indeed, we were very happy to confirm that in our rapid classification, we were able to predict within a couple of hours the seabed conditions correctly. So here's then the comparison actually to the shear strength, where you see two examples of sets of deployments here with slightly different cone factors applied. And you see, but even if you shift the cone factor somewhat, you still get a quite favorable result. So that means even if you would choose the 12 as the cone factor here on the left, or if you would just go a little bit lower based on a different calibration here, you would still get results that are very close to actual the measurements from the lab. So the field demonstration confirmed that the seabed area can be classified based on the portable freefall penetrometer deceleration data and geomechanical properties, and that can be conducted just within hours of data collection. What was one of the big goals, that this is actually a rapid seabed classifications option. So in overarching conclusion, one portable freefall penetrometer data analysis framework can succeed to assess key geotechnical properties for a wide range of seabed sediments. If you remember the flow chart I showed, so what we are applying here now is practically, even if you only have the portable freefall penetrometer data, you are able to work practically along this framework and get practically geotechnical properties out from that. And the advanced framework enables a rapid geotechnical seabed characterization that is relevant for multiple processes that are of interest for UXO site assessment and management. So let me finish up to looking a little bit into the future, and I've already pointed at some of these things occasionally. The one thing that we haven't had the chance to look at in detail, but we certainly noticed, and we're excited to report that we will look into this more through our future project, is the role of benthic biogenic processes. So if you look here at the right side, you see an X-ray image with some clamps in there. And you not only see the clamps, you also see how the clamps were digging through the sediments, clearly changing the structure. So our collaborator, Kelly Dorgan, provided me with a figure here on the left that conceptually demonstrates how different benthic biogenic processes may actually affect like cone penetration resistance for mud as well as sands. So this is something really important, and we are looking forward to investigate this a little bit further and then also integrate this into our data analysis framework. Another important aspect I pointed at how these different properties we are determining are related to geoacoustic properties, but we want to bring this a little bit more into a direct application as well as a direct relationship. So this is a figure that our collaborators, Trembonis and Carter Duval, provided to us in a joint field work in Delaware Bay. So you see in the center the side scan sonar image, and there's two sites actually highlighted, one in this yellow box on the left, and then on the pink box on the right. And then you see the associated penetrometer profiles on the left and the right, also indicated with these colored boxes. And you can see that both sides are appearing differently in the side scan sonar and are appearing extremely differently in our penetrometer results. However, all these different lines in these penetrometer profiles are in fact independent deployments, and you can see how consistent the site is, however, how different the two sites are. So we want to do more of this and bring this really closer together. Another thing we want to continue working on, we have already started working on, this is with our collaborators, Grace Messer and Karl Friedrichs, who are looking at erodibility here. So what you're seeing here on the right-hand side are plots where we looked at the eroded mass versus the applied shear stress. And you see that different sites had clearly different responses here. And those different responses are also in line with where we saw differences in the penetrometer profiles here, specifically for the example of the Potomac. So we want to, again, take the next step and actually establish here the correlations to erosion, but then also look a little bit more also into this topic of liquefaction. And then finally, we feel that it would be advantage to move our data analysis framework into a probabilistic framework and soil behavior type classification, specifically to also address this question of uncertainty for these different measurements and provide practically an assessment of uncertainty with our results. So just some thoughts about the benefits to the DoD. So a rapid in situ seabed assessment method is relevant for a number of things. We are hoping that we can contribute with this to the calibration as well as validation of acoustic seabed surveying. This can be helpful. Having these properties can help modelers and people who do impact prediction. We can hopefully provide the specific measurements so that the impact prediction can actually be based on the on-site measurements. And similarly for the burial prediction. And then also the risk of exposure from erosion here in the munition response. So thank you very much for your attention. I'm happy to take more questions, but I would like to also acknowledge your collaborators as well as my students who helped obviously collecting a lot of the data, as well as a lot of the SERDP munition response performance, as well as leadership who provided collaborations and discussions and assistance throughout the whole project. And we would not have gotten to these results without all of these discussions and help and collaboration. So thank you all really for this. And here are some additional resources, and then I take more questions. Thank you.
Great. Just a reminder for everyone, these slides are posted on the webinar webpage. You can go and download them now. And be able to look not just at the additional resources that Nina has provided on the next few slides, but also on her project webpage, which will include links to other materials associated with her project. So with that, we did receive a whole bunch of questions. So I'm going to start with one from the NATO Munitions Safety Information Analysis Center. Is your work linked or cooperative with international organizations such as NATO that are informed about the specifics of submerged munitions? And if so, can you name a few of these cooperative organizations, Nina?
So we have not directly collaborated in that case with NATO, for example. So one figure that I showed, like one of my older ones, that was on the expendable penetrometer was actually on an old NATO data set of expendable penetrometer deployments. So at that time, I was actually working at the FWG in Kiel, and we are also obviously very interested in international collaborations, but currently we haven't been really doing much direct collaboration with NATO here. But there's certainly interest, yes.
Great. This next question is from the Woods Hole Oceanographic Institute. Can you comment on the role of porosity and how this might be determined from the measurements, possibly supplemented with a grain size analysis?
Yes, so here I would like to distinguish between sand and fine-grained material. So the sand is actually pretty straightforward, thanks to the fact that we have these really, really promising results regarding the relative density. So you're absolutely right. So if we have the grain size, we can actually establish on one slide, I don't have the slide number at hand right now, but so there's this figure of deceleration versus relative density that we established through controlled tests in a large cone penetration calibration chamber. And so we got a really good match there. And that was for a medium nearshore sand. And that would cover, we have actually tested it on some variations of grain size. So it covers actually quite a range. However, it would get very coarser or much finer. You would have to recalibrate that. However, the relative density, as it actually reflects practically a measurement of how dense or loose is your packing within the range of what this certain grain size range can actually realize, is practically directly related to porosity. So there we are actually very confident at this time. On the fine-grained materials, there is a relationship between the porosity and bulk density from the undrained shear strength. However, we actually see a lot of potential coming from the coefficient of consolidation from the dissipation measurements, because we got these really good results from these initial dissipation tests that we started playing around with a couple of years ago now. And so that would be, is directly related to permeability, and then would also be a really good measure here of porosity. And then we could combine it practically with undrained shear strength, and by using then pore pressure and practically the deceleration measurement, that would probably put also, or we're expecting that would increase the confidence there. So I would say we are not really 100% there yet, but we have everything, we have the tools to put it together and get there very soon.
Wonderful. Thank you for that very thorough response. This next question is from HR Wallingford. Presumably the data is still logging as you retrieve the penetrometers. Does this data give you any anecdotal information, such as the amount of remolding in cohesive sediments?
Yeah, that's a really great question. So currently it does not. So we do indeed log all the time. In fact, we actually switch it on whenever it's most convenient, and the probe logs at least 8 hours with 2 kilohertz. And so we leave it on during retrieval. However, our measurements, like during pulling it back, we don't really get it. It's not with a T-bar, you would actually be able to measure, like during the pullback, more information about the remolded strength. In the current version of the probe, we cannot really do that. However, there has been consideration to maybe change some things to the design, or maybe do some add-on aspects that could make that possible. So right now, the only thing we really use the consistent data on is to check on the pore pressure system if we see some clogging. But there could be some potential with fairly straightforward changes to the probe.
Great. All right, and then one last question for you. How do you envision, from a practical perspective, implementing the use of these portable Freefall penetrometers for submerged unexploded ordnance site characterization, assessment, and management? So big picture, as you take your results and try to think about applications.
Yeah, so I see different pathways depending on also the site-specific conditions. So obviously, everyone would like to avoid like dropping it on something risky, in particular if we're expecting them to be shallow. However, in many cases, you will have similar soil behavior very nearby, where you could deploy and practically use this data directly to characterize and then also predict the likelihood that an object has sunk in deeper, that objects may have sunk during a storm from liquefaction, or may have gotten buried, or may get unburied during the next storm or more energetic event. And then I also really see a great potential connecting it to acoustic methods, to actually really make the connection here, to take advantage of the more remote acoustic sensing, but take advantage of our measurements to really provide a calibration from the geotechnical properties side, so that then from the acoustic surveying, you can go even further than determining sediment type, but maybe even expand and extrapolate more confidently from our point measurements what are actually the geotechnical properties, what then again could go into models for the impact prediction or the burial prediction or erosion and so on.
Great. Thank you so much, Nina. This was an outstanding webinar. We're going to go ahead and try and wrap up here and remind everyone that the slides are available now, and a recording of this webinar will be available next week for download. Our next webinar will take place on Thursday, September 9. It's a joint environmental restoration and weapons systems and platforms webinar on managing aqueous foam-forming foam impacts to subsurface environments and the assessment of PFAS-free foams. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. We would appreciate it at this time if you could please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you for your attention, and thank you, Nina, for an outstanding presentation. Thank you.
Thank you.